All right, let's start off with how to evaluate these guys. And I mean, there's maybe a little bit of work we could do by hand, but not much. And you're just going to end up on the calculator anyway. So let's do it. So, all right. So we got a couple of buttons on the calculator that'll come in handy. One of them is log right there. Okay. And that button means log base 10 because there's different bases for logarithms. But this, if you want base 10, that's your button right there. It's just the base 10 is built into it. Or you could go alpha, window, and then notice option 5 is any base you want. You could still do base 10, but yeah, that's how it goes. Now, on this first one, it just says log 21.1. Okay. Now, normally it's going to say something like log base 3, or well, I'll do 2. Log base 2 of 21.1 or something. And the base is that little subscript down there. But this one doesn't have that. There is no little subscript right there. When you don't see the subscript, that means that it's going to be base 10. So no subscript means base 10. All right, so I'll go 10 of 21.1, and I get that. Or I could have, like I said, just done log base 10, 21.1, like that, and I get the same answer either way. So what does the answer mean? It means that if you do, if you do 10 raised to that power, you'll get 21.1. Okay. And we could certainly double check that. We could say, all right, well, let's go 10 raised, and then I'll grab that guy to that power. Does it give me 21.1? Sure. It's off ever so slightly because this number here is rounded off, but like at like 9 decimal places. If this number were absolutely perfect and not rounded off at all anywhere, then yeah, this would give me exactly 21.1. So that's what's going on. Okay, on the second one, it doesn't even say log. Okay, it just says ln. What the heck does that mean? I'm glad you asked. So ln of root 3 means log base e of root 3. So ln means log base e. So this is the only other kind of shortcut where they don't explicitly say what the base of the logarithm is. Well, what the heck is e? Well, just like pi, that's 3.14, and it goes on forever and it never stops or repeats. E also is an irrational number, and it's about 2.7 and blah, 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 and it goes on forever. Okay. Now on their calculator, we got the ln button right here, and we could say, all right, square root of 3, and we get that. So just like on the last one, if we do the base of the exponent, e, raised to this power, that should give us square root of 3. Okay, well, let's try it. Notice right above the division sign is the E button. So I'll go second division, raised to that guy there. And that should be equal to square root of 3, and indeed they are equal. And on this one, the slower way of doing it would be alpha window 5, typing the E, and then doing the square root of 3. And, I'll give you the same answer. It just takes a couple extra keystrokes is all. But that's how it's done. Now, in order to work effectively with logarithms and exponential equations, especially logs, you have to be able to convert back and forth. Okay, so this equation is in exponential form because I see an exponent, the 5. And so I can rewrite it as log base 2 of 32 equals 5. It's probably not obvious at the moment why we might want to do that. But if one of these three items was a variable, that might help us to isolate the variable where we might not be able to otherwise. But yeah, log base 2 of 32 equals 5. And that's how it goes. So you'll notice that the base of the exponent, the 2, that becomes the base of the log. And then these two guys here switch places, 5 and the 32. Okay. And it looks like that. So, and of course we can check that on the calculator. We can say, all right, does 2 to the 5th power really equal 32? Yes, it does. All right. So the original equation is, actually makes sense. Okay, what about log base 2 of 32 equal 5? Does that really work? Alpha window 5, and that should equal 5, and indeed it does. Okay, so we got that. What about the other one? Well, on this one, we start in log form. We're going to end up in exponential form. So remember how the base of the exponent becomes the base of the log? They're always the same. Well, okay, so the base of the log becomes the base of the exponent, and the other two guys swap places. And we know this is a true statement because anything to the 0 power does equal 1. So make sure you practice real good being able to convert back and forth between log form of an equation and exponential form of an equation. Now this topic, same thing, except instead of just any old log, it's natural log. Natural log means where the base is e. Okay, so whenever you see ln, we know it's log base e, and that is called the natural logarithm because it has a base of e. So you could say, well, it makes me feel better to write log base e of x equals 6 and explicitly see that e. All right, whatever. You don't have to write it that way if you don't want to. And then we just convert to exponential form. E to the 6th equals x. And this one, log base e of y equals 7, or the cool kids will write ln of y equals 7. Okay. So why might you want to do this? Well, like I said a moment ago, maybe to isolate a variable. For example, on this first one, you've got there's a variable in there, but how do you get it out of there? I mean, it's not ln times x. It has nothing to do with multiplication. So if you convert to the other form, now you have extracted the x, and it's now isolated, so you can solve for it. Whereas at the beginning, not so much. On the second equation, well, there really wasn't any real reason to convert it except because they said so. The variable was already by itself, the y. E is not a variable, okay? It doesn't vary, it doesn't change in value. E is always 2.8, blah, blah, blah. Okay, now these, I know you can do them on your calculator with that alpha window 5 thing, but they on this topic, they set it up so that you don't have to, that you can actually do them by hand. The numbers work out real slick. And the basic idea on these is if you have something like log base 5 of 5 to the 2nd power, then the answer is 2. Because if the base of the exponent, or I'm sorry, the base of the log, and then this number here, if they match, then the exponent is going to be the answer. So that's kind of the idea. So on this one, you could say, well, that's log base 8 of, well, let's rewrite 1/8 as 8 to a power. Well, that'd be 8 to the -1 power. So my answer is -1. And you can double check on the calculator, alpha window 5. For the second one, we've got a base of 3. So let's write 81 as 3 to a power. Turns out it's 3 to the 4th. So the answer is 4. That's how it's done. Okay, on this one, we're graphing, but you're being asked to graph on Alex. So they're only saying, you know, you only need 2 points. So I don't know, let's pick 0 and 1, I guess. Those work pretty good. Okay, so g of 0 is going to be negative log base 3 of 0 minus 3. Let's see. It turns out, let's see. Oh, that's actually not going to work, is it? Okay. Rats. That's, yeah, it's just going to be undefined. So let's skip the 0 and let's just go straight to the 1. Okay. And so that'll give us, let's see, log base 3 of 1. That is 0. And then we get negative 3. All right. And I'm going to, because I'm familiar with logs, I'm just going to pick numbers that work real nice. All right. The next one is, let's do x equals 3. Okay. So if we do g of 3, well, log base 3 of 3 is equal to 1. And we get negative 4. Okay. Now they say to graph it on the calculator. All right. Well, I'm going to do it by hand, kind of wing it by hand a little bit. First, whoops, that is not what I wanted. So if I do it by hand, it's going to look approximately like this. We got a point at 1, negative 3, and a point at 3, negative 4. So looks like we're going to do maybe something like this, because I know what I'm familiar with log functions and stuff. Okay, and then it says, oh, don't forget to do your asymptote. Now, for the basic log function has an asymptote of the y-axis, the line x equals 0. Okay, it can't go there. That's why when I plugged in x equals 0, I was like, uh-oh, that ain't gonna work. Okay. That's supposed to be a sad face. I was going happy. Whoops. Let's check it out on my calculator, because I mean that's how you're going to do it anyway. You're going to use the graphing feature on Alex because, well, they ask you to. So we got that, and so if we go zoom 6 to see the basic graph, yeah, it looks like that. Now, it looks like the function just sort of stops, and we've seen things like that before, but it actually keeps going, okay? It just gets so close to its asymptote that the calculator can't really distinguish, and then it just stops graphing it. So, but that's what is actually happening, okay? Now, I had a really good idea of what this thing was going to look like, not just from those points, but mainly because the function, well, the basic log function looks like this. Comes in and looks about like that, uses the y-axis down here as an asymptote, just gets closer and closer. Okay, but our function was negative log base 3 of x minus 3. And so I said, well, you know, you stick a negative in front of a function, and that just flips it over. So it flipped it from this to this. Okay. And then this minus 3 right here, all that did was just shift the whole thing down 3 units. Okay. So there was no horizontal movement of the graph. Therefore, the vertical asymptote was not shifted one way or the other. It just stayed where it normally is on the y-axis. Okay, now what about the domain and range of the function? Well, there's a lot of mess there, isn't there? Maybe I can make this a little easier to see. Pretty much all of those we don't need. Okay, there we go. That's a little better. So the domain is going to be, it doesn't ever hit the x-axis or the y-axis, but it's everything on that side of it. It just gets closer and closer to the y-axis. So it's using x values that are greater than 0. Not 0 itself, because that would be the y-axis, but everything up to it. And it says do it in interval notation, so that would be everything from 0 to infinity, written like that. Now what about the range? The range, well, it goes up infinitely high, and it goes down, and it just keeps going down lower and lower, really slowly. These log functions, they don't go down on this part of the graph. They don't go down or go up really fast at all, but they do keep going down forever. So it's just going to be negative infinity to infinity. Everything. Yeah. As high as you can go, as low as you can go. That's the range. All right, find the domain of the log function and give interval notation. Okay, so what are we allowed to plug in for x? Well, we usually start with what we're not allowed to plug in. And well, we all know that, or should know that, denominators are not allowed to be 0. It doesn't really make sense to divide by 0. I mean, it doesn't make sense to, if you think about it. So x minus 2 cannot be 0 is what we're saying. Or x cannot be 2, and that's the domain. Okay. On the line graph, it looks like this. Everything's shaded in except 2. So that would be negative infinity to 2, and from 2 to infinity. Notice that shows the same thing. So 3 different ways of expressing the solution. That's the one that they asked for. All right, so let's try one more of these. All right, so this time there is no denominator. So we don't have to worry about the denominator being 0 because there is no denominator. However, unlike the last problem, remember that when you the basic log function looks like that, and it never touches the y-axis. Okay, so it has to always be positive. Okay. Whatever's being plugged into the function has to be positive. Okay, so we don't have to worry about the whole denominator thing, but we do have to make sure that thing is positive. So in other words, the square root of 2x plus 5 must be greater than 0. It's got to be positive. Okay, so that's where we're headed on this one. Now, in order for that to happen, the stuff inside of the square root has to be positive. Okay, and therefore, if we add or subtract 5 from both sides, we get that. Divide both sides by 2, we get that, and therefore that would be the domain. Okay, we're allowed to plug in anything, any number that's bigger than negative 2.5, the negative 5 halves. In interval notation, that would look like that. Okay, and we got it. And I will point out that in that last example, the one that's no longer on the screen, I did make a little mistake. I made sure the denominator was not 0, but I didn't make sure the entire fraction was positive. And I apologize for that. Unfortunately, I can't go back.